Hello, ladies and gentlemen. Welcome to Math 20-2, Chapter 1, Section 1, Part 1, Making Conjectures and Inductive Reasoning. Now, the objective today will be making objectives by observing patterns, and identifying properties and justify the reasoning. Now, inductive reasoning is fairly straightforward. We start with an observation, specific observations, to be more precise. Then we note the pattern, we detect the pattern. We have a tentative hypothesis, that is, we collect evidence to support our idea. Then we develop our theory or general conclusion. Now, important here, drawing a general conclusion by observing patterns and identifying properties in specific examples. Sorry, that's the definition of inductive reasoning. Drawing a general conclusion by observing patterns and identifying properties in specific examples. Now, let's do an example here. The last 3 Halloweens in Slave Lake it has snowed. Halloween 2019 it snowed, Halloween 2020 it snowed, Halloween 2021 it snowed. Based on this pattern, we can assume that it will snow in 2022. In other words, we can use inductive reasoning to make a conjecture or educated guess that it will snow in 2020. Okay? So that's what I want you to think about conjecture, educated guess. All right? Probably the best way to think about it. Now, examples of inductive reasoning. Inductive, the missing word, sorry. Now, conjecture. Conjecture is an educated guess based on observation. So, let's study the diagrams below and make a conjecture about the number of triangles that would be in figure 100. No, sorry, you should have the paper, but here's the pictures of them. So, you're making a statement based on examples. This is inductive reasoning. Based on examples, inductive reasoning. Sorry. Now, here we have to do a little bit of thinking. So you see 1 triangle, then you see 2 triangles, then you see 3 triangles. Okay? Now notice what's happening here. Okay? Now, there's a pattern forming here, and it might be helpful to actually make a list. So the way I would do this, being a math teacher, I go row, and then I go number of triangles. So I'm looking for the pattern. Remember? We went back here. Observation, pattern, tentative hypothesis to come up with a theory. So we're observing something. Let's see if we can come up with a pattern. So our observation, row 1 has 1 triangle. Actually, color code, Mr. Sutton. Row 1 has 1 triangle. Row 2 has 1, 2, 3, 4 little triangles. Now, notice I said little triangles. Okay? So row 3, or number 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So, what have we got here? Well, we have a pattern. 1 is 1, 2 is 4, 3 is 9. Now, here I get lazy. I go on. What will my next one be? Well, here I want you to note 1 to 1, 2 to 4, 3 to 9. That's 3 squared. That's 2 squared. That's 1 squared. Now, if I had the space, and I did like to think I gave you enough notes there, enough space there, we go on to 4. Can I fit 4 in here? 2, 3. Can I cheat? 1, 2, 3, 4, 5, 6. Horrible triangle, but you get the idea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, row 4 is 16. So there is a pattern there. All right. So that is coming up with the tentative hypothesis. So my theory is row number squared equals number of triangles. So row 100 will be 100 squared triangles, which is 10,000, I believe. Okay, now that's a straightforward-ish one. All right, so far so good? Yes, I should draw a better triangle. Now, so next example, let's make a conjecture about the product of two integers. Now, conjecture, let me see, educated guess. And product means we multiply. Now, integers are whole positive numbers. All right, so just remembering the definitions. Actually, I have to write them out because I'm old and I forget. Anyway, so 1 times 7 is 7. 8 times 5 is 40. 3 times 11 is 33. Now, what can we say about all of these? 6 times 5 is 30. Now, as I said, I'm just making this up. So I'm going to go 12 times 6 is 72. Now, we have an integer times an integer. What's our product? What can we say about all these products? Well, some of them are odd, 7 and 33, and 7 and 33. Some are even, 40, 30, 72. 7 is prime, that is. It's 1 times 7 is 7, but 40's got lots of factors. 33 isn't prime. No. Well, the only thing I can say is all integers. The product of two integers is another integer. Because we're not making fractions or decimals, negative numbers. Yes. So that's, yes, I think so. The product of two integers is another integer. Now, of course, remember, using this inductive reasoning, observation, pattern, tentative hypothesis, it never hurts to come up with a couple more examples. So I'm going to go 6 times 11 is 66. 2 times 35 is 70. Yeah, we're still getting integers. I'm relatively happy with that. All right, so here we got some mathy thinking. Now, let's do one more example in this part of the video, and then we'll go on to do something else. So, make a conjecture or educated guess about the difference of two perfect squares. Now, remember, perfect squared is like 6 squared minus 3 squared. That is 36 minus 9, which is 27. Okay? Now, pulling these numbers out, 25 squared. Now, notice I'm going a larger number. The difference, I'm subtracting one from the other. I've decided that I'm going to subtract the smaller from the bigger. So that's 625 minus 49 is 576. Now, just pulling out some perfect squares. Now, I did that kind of quickly. I did this with a class previously, and those are the numbers we got. So what can we say? What's an educated guess about the difference of two perfect squares? Well, we look at our answers. What do we got? 27. Okay, let me see. Some are odd, some are even. 25 is a perfect square, but 27 isn't. 6. The only thing I can see is difference is an integer. Now, once again, using inductive reasoning, we made some observations, or an observation. Now we're looking for patterns. And tentative hypothesis, or educated guess. And theory or general conclusion. All right, so theory is the difference is an integer. Now in a later lesson, I'll show you how to prove this. If you want to, actually this video is getting kind of long, but if you really want to do it, find another example. Pull out another example. 7 squared minus 2 squared is 49 minus 4, which is 45. Yes, is an integer. So I'm happy with that hypothesis. Or I'm happy with that theory, I should say. Now, this video is getting kind of long. I'm going to pause it here. If you've got any questions, watch the video again, look at the examples, or shoot me an email. Otherwise, good luck. We'll go on, and I'll see you in the next video.